Okay, so what happens when we do k equals 2 is we come out of this, we break this rule, this tradition of having the angle that I've been describing in here, or also depicted by theta, which goes anti-clockwise round from this value of 0, and it needs to be between minus pi and pi. I'm not sure why there's not a space in here, I need to sort that out. But this is an issue because what we end up with is 4/3 pi, which is too large. So what we're going to do instead is we're going to say, therefore, for k equals 2, we have a problem. What we do is we say nah. We say no. When I'm using the word out of range, I'm not using it in terms of range and domain. I'm just suggesting that in terms of language, we're outside of what we have described as our boundaries. What we should do instead is when k equals, we're going to try -1. And notice for -1, we get minus 2/3 pi plus I sine minus 2/3 pi, which gives you this here. And that is something that can be described that is within our range here, and therefore for arg is acceptable. And what I just said is I've noticed how this problem is easily solved when trying k equals -1. It is advantageous to check the negative values of k if you find that you hit the boundary. Trying other values of k might violate the definition of arg, and or you could consider it as producing equal outputs round the argand diagram. This leaves us with, and I believe this takes us to my next page, this diagram here, which we can analyze in a bit more detail. So there is our 1. You can see there's the one we found. There is that there. We've got the one that we found second as a result of k equals 1. This one was k equals 0. And finally, we have our new one as a result of k equals -1, not k equals 2. That left us out a little bit. And so we have our three roots. And these all are solutions to or solve the puzzle as to what z cubed equals 1 actually can come in terms of a form that can be placed on a diagram, and these can be described as the solutions to it. Anyway, what I've described here is I said you've got 3 roots. They are all equally spaced, and this is something that's interesting to recognize. That angle there, let's see if I can use my paintbrush to a better technique. There you go, that's not bad. It's 2/3 pi. This here will be 2/3 pi. This here, if I went from this side, would be minus 2/3 pi. And so they are all equally spaced. There are 3 roots, and they all solve the problem of what values, what complex numbers fit the idea of z cubed equals 1. Let's move on. What have I said? I've decided to make a statement. I said the term roots is used to describe the complex numbers depicted in the diagram. There are 3 of them. The diagram above illustrates 3 roots born from z cubed. The same steps can be followed for z squared and z4. Please have a go at the same concepts. To aid in understanding, you will find that for z4, you will have 4 roots that come about. Okay, so let's look at this in another way. One other way to view this is by considering it in terms of lying within a circle. The circle is of radius 1, as the result of the first one being 1, and all of them from then on staying within that value. The concept here is that they all have exactly the same modulus, and so we can also call it the radius circle of radius 1 unit.